Good day and welcome back to our second installment of introducing functions of multiple variables. In the previous video, we introduced some of the basic properties, such as domains and ranges of a function. In this video, what we'd like to do is concentrate on the visualization. What does the graph of a function of two variables look like? So to begin, we say that the graph of some function of two variables is going to be a set of points of the form x comma y comma z in three-dimensional space, such that the points are related by the fact that z would be the output associated to the input of the pair x comma y, and xy is in the domain. And this is a great opportunity just to give us the reminder that for a function of two variables, we think of the input as being some pair in the xy plane, and the output is a number. And before diving directly into an example here, let's just kind of make the connection back to our previous experience. Previously, we would think of the function y equals f of x, and we would think of the graph as being made up of all of the points x comma y, with y equals f of x. So the same exact idea now in three dimensions, it's just that the third coordinate z is the output we get from inputting that pair x comma y. So a common question that we could ask then is to sketch the graph of some function of two variables. And let's revisit our example g that we discussed previously. And in order to sketch the graph of a function of two variables, we in some sense need to recognize kind of what a corresponding surface is going to be. So to begin, what we can do is simply write down z is equal to our function. So we can start off with z equals g of xy, so the square root of 9 minus x squared minus y squared. And the question is, what does the graph of this surface look like? And we can certainly go back to our previous methods dealing with quadric surfaces and traces, but instead let's see if we can get maybe a familiar object to come from this. Now the first thing I'm going to do is kind of just make an observation. Z is the square root of a quantity, which means it must be bigger than or equal to 0. And that's not surprising in the sense that we saw in the previous video. The range of this function is the closed interval from 0 to 3. But if we manipulate this, we could square both sides to make it look simpler. We could add x squared and y squared to both sides to make it look familiar. X squared plus y squared plus z squared equals 9. And this represents the equation of what type of object. And hopefully I'm agreeing with you here. It represents the equation of a sphere of radius 3 centered at the origin. But remember our observation that we made above, it's not the entire sphere. It's only going to be the top half. So only the top half, because we need to satisfy this relationship we observed above. And this is something that we can easily graph. The top half of a sphere of radius 3 centered at the origin. So think of this kind of as the upper hemisphere. And then labeling those positive intercepts, we'd have 0, 0, 3 on the z-axis, 0, 3, 0 on the y-axis, and then coming out of the screen towards you, we have 3, 0, 0 on the x-axis. And note the key to sketching the graph of this function of two variables is recognizing that it corresponds to this portion of a sphere. So I'm going to go ahead now and jump in that note packet to the third sheet, and we'll come back to the example on the bottom of the second page in our next video. I want to keep these two related examples together. So the method for sketching that we used in this first example was really to look at that function, set it equal to z, and think really hard back in terms of things that we've seen in the past. And if you don't see the fact that this is corresponding to a sphere of radius 3 centered at the origin, it becomes awfully difficult to sketch the graph. So sometimes it's going to be useful to have a more methodical approach. And the more methodical approach is to use quantities that we refer to as level curves. And the level curves of a function of two variables are the curves of the form f of xy equals k, where k is a constant. And the big observation is that this is not a new thing, that the curves of the form f of xy equals k, where k is a constant, these are the z equals k traces. And we can sketch those z equals k traces, and they will form what we end up calling a contour map. So for this function we've been working with in our previous examples, g, let's go ahead and find and sketch the k equals 0, 1, 2, and 3 level curves. And instead of working individually with the k equals 0, 1, 2, and 3 values, which we certainly could do, we are instead going to think about a general k and see what that gives us. That is, what does the graph of the curve g of xy equals k look like? G of xy is the function the square root of 9 minus x squared minus y squared. If we square both sides, we would have minus 9 minus x squared minus y squared equals k squared. So that by regrouping these, 9 minus k squared is x squared plus y squared. And as long as this quantity that we see on the left-hand side is positive, we will have a circle centered at the origin whose radius is determined by the square root of that positive quantity on the left. And note immediately that the fact that that quantity on the left needs to be positive, that's restricting the values of k that we can deal with. This is telling us that k must be bigger than or equal to minus 3 and less than or equal to 3. Let's now focus on the four values of k we've been asked to sketch. So to begin, if we have k equals 0, and I'm simply going to kind of cut and paste what we have to the left, but I'm going to substitute in that value of k. So when k is equal to 0, we have x squared plus y squared equals 9. And x squared plus y squared equals 9 would correspond to a circle of radius 3 centered at the origin. And as usual, remember these pictures and graphs do not have to be perfect. Far from it. They just have to get that relevant information across. And since we're going to be sketching several curves, I do want to indicate each one with a labeling of the k value. So k equals 0 to start. The next value, k equals 1, would be the graph of x squared plus y squared equals 9 minus 1 squared. That is a circle of radius square root 8 centered at the origin. I don't necessarily have a good idea of the precise value of square root of 8, but what I know is it's a number between 2 and 3, and closer to 3 than it is to 2. So let's go ahead and place it right about here. And we have circles which are centered at the origin. So this would be k equals 1. And just to get that in there, I'm going to erase a little bit of the curve and just substitute in here k equals 1. For k equals 2, just playing the same game over again, x squared plus y squared is 9 minus 2 squared. So 9 minus 4 is 5. A circle of radius 5 centered at the origin. And square root 5 is a number a little bit bigger than 2. So roughly speaking, and I know these are not perfect, and remember, they're not required to be, the graph would look something like this. So this would be k equals 2. And then lastly, in terms of what we've been asked to find, we have k equals 3. And the k equals 3 level curve would be x squared plus y squared is equal to 9 minus 3 squared. So 9 minus 9 is 0. Note x squared plus y squared equals 0 describes precisely one point. X and y both have to be 0. So this would be k equals 3. Now that we have all of these level curves drawn together, let me note that this is something that we refer to as a contour map. And contour maps are familiar things. Think topographic map, where each level curve is indicating a specific elevation. Now, the big question is, how do we go from one of these contour maps to a surface? And let me show you the relationship that we can hopefully see with the work we have, and then I'll even embed a GeoGebra file to see it hopefully as clearly as possible. So if we start off with k equals 0, this would correspond to the z equals 0 trace. So we're thinking that circle of radius 3 centered at the origin would be where the graph intersects the z equals 0 plane. The k equals 1 level curve is the k equals 1 trace. It's where that graph intersects the z equals 1 plane. So we're seeing it as kind of an elevation curve in our graph. Then we have z equals 2, and we have z equals 3 being this solitary point, in a sense, right up at the top of the hemisphere. All right, so now that we've seen this illustrated with my hand-drawn images, let's go ahead and embed a GeoGebra file that will more clearly demonstrate what is going on. And what we are now seeing is a GeoGebra file illustrating the surface of interest. So it's a top half of a sphere of radius 3. I'm going to rotate it around so that we are now seeing kind of the domain. The range would be all possible outputs in that z direction. And now to get the level curves in there. So we're going to start off with that k equals 0 level curve, where it intersects the z equals 0 plane. The k equals 1 level curve, where it sits 1 unit above the xy plane. K equals 2, and k equals 3. And the bird's eye view of this is really going to show us kind of the corresponding contour map that we created. And hopefully what this does is helps to show you the connection between the graph of a function of two variables and that associated contour map. And moving forward, we can think of using these level curves or these z equals k traces as a tool that allows us to get a better idea of what the graph of a function of two variables will look like. In our next video, we will investigate several more examples dealing with 1, graphs of a function of two variable, and 2, just contour maps in general. So stay tuned and take care.